So these are our applications of rational functions. And what we're going to be using is that whole idea that if we have a top degree that is smaller than the bottom degree, so basically this, the limit of our function of bigger over smaller, not smarter, smaller is equal to 0 as x approaches infinity, right? And so our limit as x approaches infinity of 1 over x is going to be 0. We're going to be using this rule. So we already knew that this is just a fraction. It gets smaller and smaller as a fraction, and we get 0. So in each of these are going to be getting set that kind of an idea, and we'll be applying it. So let's look at our first one. We have our cost function here, and so x is the number of toothbrushes, and c is the cost. So it's the cost to make that many toothbrushes. So they have some $250,000 worth of startup costs. And then it's 45 cents a toothbrush to make these. So what we want to do is find the average cost then of our toothbrush, some function that tells us the average cost. So to find average cost, you take a of x, we'll put AC for average cost, like that. And so all it is the cost of the function, the cost function, divided by x. So what we're doing here is taking our costs to make a certain number of toothbrushes, and then dividing it by the number of toothbrushes we've made. So if you made 10 toothbrushes, you'd plug in 10, and then you divide it by 10 to tell you the average cost of those 10 toothbrushes. It's just our average formula. Total cost divided by the number of toothbrushes. So if we simplify this, we get 0.45 plus 250,576 over x. And so that is our average cost. So now the question is, find the limit of the average cost as our x approaches infinity. So this means if you make a lot as you approach to making an infinite number of toothbrushes, which doesn't really exist, but you can think of it as billions of toothbrushes, what happens to that fraction? So anytime you see that x is bigger on the bottom, we get 0. So our limit here would be 45 cents. What this is saying is this is why big box stores will blow away any small store, is it doesn't really matter. I mean, it does matter a little bit about how much, but if their startup costs are a lot to create these toothbrushes, as time goes by, they are going to make billions of them. And so what happens to those initial startup costs is they just basically disappear, and it really is the cost per toothbrush. So while smaller companies are going to have to include this number into their actual cost, big companies can basically exclude it and just charge based on the cost per toothbrush. So if they charge 50 cents, they're making 5 cents. And if you think that's not a lot, they're going to sell a billion toothbrushes. So it turns into a lot. They can have very small markups, large costs to create something, and still make crap loads of money. So let's look at another one. So the population of a community is given by this function. So they figured this function out to be the population of the community as t goes on in years. So now we ask, what can you expect the population to be in the long run? So that's just another way of saying the limit as time goes to infinity of our function. And all we're looking at is just when is the top degree smaller than the bottom. So the first one, top degree is bigger than the bottom, than the top. Top is smaller than the bottom. This goes to 0. Top degree is bigger than the top. This goes to 3. So big bottoms. Big bottoms go to 0. So what number are we left with? 70. And now we just need units. So we're assuming this is the population. So there would be 70 people. That's kind of depressing. So this town is disappearing. So in the long run, there will only be 70 people left in this town as t goes on and on. So how about this one? So this is the one that I really like. This gives the body concentration N of t in parts per million of a certain dosage of medication over time in hours. Find the body concentration in the long run as t approaches infinity. So if you notice on this one, we say limit as t approaches infinity, but I've changed the function now. So we're not dealing with big bottoms. I actually like that, big bottoms. It's easy to remember now. If it's got a big bottom, it goes to 0. So the bottom's bigger, it goes to 0. So here we go. On this one, the t's are the same. So we have the same degree. And if you remember with the degrees are the same, It's just the leading coefficients. So we end up with this. So it's saying that the body's concentration N of t in parts per million of a certain dosage of medication after time t in hours. Find the body concentration in the long run as t approaches infinity. So as t is approaching infinity, this is going to this. So the body's concentration in parts per million of this medication is not disappearing from the body. So if we divide this in our calculus, we end up with 0.16. So 0.16. And then we got to go back and find our units. We didn't write that on this one because the rest have been pretty easy. So t here is number of hours. And n of t is parts per million. The concentration, parts per million. So what we end up with here is parts per million. So this drug dosage, whatever they've given, it's not going anywhere. There will still be 0.16 parts per million left in the body as t approaches infinity. So forever, you take this drug, it's always going to be with you for the rest of your life, a part of you. So that is how we use it. So if the t's are the same degree, we just use the leading coefficients. And if the bottom's bigger, it goes to 0.